Hello everyone, my name is Aman Bagrecha. So I'll be talking about monitoring blue sky, monitoring water bodies within the land. So let us begin. So I work at Blue Sky Analytics. So Blue Sky Analytics is a geospatial data analytics company, primarily focusing on monitoring all aspects of the earth, be it land, sea, ocean. So we basically focus on creating data sets for climate risk analysis. I'm also an organizer for Let's Talk Spatial Meetup Group, which is based in Bangalore, India. So we hold meetups every month and organize these kind of meetups. We invite speakers and ask them to present. So it is streamed online as well. You can look out at Let's Talk Spatial. I also have YouTube and blogs at the website. And I'm also a member of IEEE GRS Bangalore section. So let us start with the objectives. I'll be focusing on two parts, which is first is why we need to monitor and how do we do monitoring and what do I mean by monitoring. So let us start by an example why we need to monitor water bodies. In the example that you see here, this is our platform, but this platform is space-time and we are visualizing one of these reservoirs. This reservoir is based in India, which is Tungabhadra Dam. This dam supplies water to many of these cities, nearby cities. And on the right you see Ballari town, which receives water from Tungabhadra Dam. When you see the curve on the right, there is a cyclic pattern. This pattern represents a multi-year time series of water levels, of water surface area. This surface area, when it decreases, you identify it as summer, because that happens during summer. So this is one of the critical requirements. You need to know when water level dries up so that you know that there is some other alternative so that we can supply water to this city. So this was a GIF, but I don't think so it will work. But what you see here is decreasing water level. This GIF won't work, but yeah, I'll move on to the next. In this talk, I'll focus on two things. One is surface extent, how do you calculate the area and perimeter, and other is the water level. By water level, I mean level from mean sea level and not the depth of the water from the baseline. So when we started building this product, so this is a data set that we created internally. We had some checklist in mind. So this was like we want to monitor all water bodies across the globe. We wanted near real-time updates and we want at least 5 years of data based on our client requirements. So we started with the first, which is the surface area. This surface area is basically your perimeter and area itself of the 2D area. The way we calculated area was primarily we use Sentinel-2, and there are like standard procedure that we follow here, which is pre-processing, transform, post, and inference. In pre-processing, you do your basic filtering of clouds. Transform is you're transforming your raster data to vector. In post-processing, you're doing noise removal. So when you convert raster to vector, there are some small patches of raster that are independent and you want to remove them. And then you do inference. But there are few challenges which I want to focus on. Challenges are that when you take a satellite imagery, optical will always, even in some amount, have, maybe not always, but it will most of the time have cloud. And that partial cloud affects your results of area. And then there is partial satellite scene. Maybe the water body is not intersecting entirely. Even when you query the satellite data, entire water body is not queried and only maybe a partial water body is queried. And then how do you validate your surface, whatever area you get? So these are the challenges. So we'll look at what specifically the challenges and how we approached how we approach the challenge. The first is partial cloud. So on the screen that you see is, maybe you're seeing some clouds here. So these clouds are just intersecting your water body shape just quite a little. And when you convert your raster, when you do a filtering, initially at the initial step, maybe you put a threshold of 5% or maybe 10%, but does not mean that that is for the whole AOI and not just for the scene that you're looking at. So this is one of the problems that we faced. What solution we approached was, you have to calculate the intersection of the calculated area of the surface and you have to identify the clouds and also the surface. And when you identify some intersection, if there is an overlap, you remove them. This was another challenge that we faced. You see a Sentinel-2 scene here. So this is one of our lakes that we were monitoring, and the lake is not being completely covered by the satellite scene. And this is again a challenge. So you have to consider that into aspect. So you can't use this satellite scene. Again, this is discarded. Another is validation. So on the platform, what we do is we don't just display the area, we also display the satellite scene itself. So we also render the satellite scene and also the converted raster with area and perimeter, so that you know that what I'm looking at is actually valid. So if I see here in the screen, here you would see some yellow patches, pink patches. So the pink patches is not recognized as water body, but is taken out from cloud. So you can see here, this representation of area gives you like an idea it gives you a validation if the calculated area is correct or not. And then at the end we remove filters. So on the left you might have seen, you should see some patches of blue. So these patches are because of, there might be some water bodies, smaller water bodies that are present, and you want to remove them as well. And there is inherent, when you convert from raster to vector, there are few noise, so you have to remove using noise processing. Now we'll focus on water level. So water level is basically, again we have the same checklist as water monitoring, because we are doing simultaneously both the surface area and the level. We want to have the same checklist in place. So basically what we are monitoring here is the water level, and I want to just clarify that. So this is the ellipsoidal height. Basically you take a reference, from there you calculate the height of the water body or the topography. We are not calculating the depth. Maybe a reservoir from here, if the water depth is here, we are not calculating from this surface, but a reference point. So a reference point generally is mean sea level for most of the reservoirs, and that is what we are going to use. In this case, we are going to use an altimeter. So there are many altimeters. For our use case, we used a radar altimeter so that it can penetrate cloud, so that we have data throughout. We can calculate water depth, which is from your actual level, but that is only possible with laser altimeter, and that too your water should be clear, so you should be able to see it through your eyes, and only up to a certain depth. So that was the limitation, and that is why we did not go ahead with laser. And also laser cannot penetrate through cloud. We had to not use it. So these are the missions, altimetry missions, which are currently in orbit. The last one is in orbit, but the data is yet to come yet. So maybe next year, I think by mid-March or May, June, we'll have SWOT data as well. We went ahead with Sentinel-3. On the right, you see the temporal frequency, and on the far right, you see the sensor, which is radar or laser. Most of them are radar, but only one of them is laser, which is ISAT-2. So we went ahead with Sentinel-3 because it is 27 days. I agree that it is quite a long period to get one single data point, but we went ahead because the track spacing is quite small. We'll look into the next slide what that means. So these are the challenges we faced for calculating water level. So parameter selection, partial subsetting and validation. I'll go into what this means. So first is parameters. I think I should first go to this partial subsetting. So all the altimeters data is in vector format, and you get just a strip. It is not a raster image that you have continuous data, but just a strip of just a line that revolves around the earth. So this is for one day that you see Sentinel-3 Saral mission revolving around the earth. And the problem is you cannot partially subset. With raster data, you have COG format, so that only if you require the area of interest, you can subset that. Here you have to download the entire data and then filter it. So that was one of the challenges, that you have to download the entire scene, entire data, even if you require just for one lake. There was another challenge, which was parameter selection. When you look at the documentation, it is not well documented. How do you actually calculate water level. On the right side, you see a small text that is done purposefully because it is quite complex. You have to identify which parameter to select. In this case, you need to know which reference point are you taking, what corrections to apply. So these things you have to actually read through and then apply corrections to finally calculate water level. That was the second challenge. Now we go to how do we extract water level. Now once we have the scene which is revolving, on the right you might see these lines. So these are your sentinel 3 seral tracks which pass over water bodies. In our case, this is one water body which is many tracks are passing by, and the other body you might have seen that there is just partial intersection and not complete intersection, and that is also a problem because you might get noise because maybe at the end the surface is quite high. The surface itself is quite high, there is no water there. So that is why that is also a problem. So what we did with water level is we first masked out all the scenes, all the tracks not intersecting our water bodies. So this is what we did. We masked out all our scenes and then just took the tracks within the water body. Then we discarded the outliers. Then you take an average or mean or whatever statistical analysis you want to do over that water body, discard the mean, discard the outliers, and the value that you get, you apply corrections on top of that. So this is the limitation. On the screen on the right you see is a felt map. You can play around when you click on the link. These are the tracks, sentinel tracks, and the distance between them is 100 kilometers. This is the highest that we have got till now. All the other satellite altimeter mission which you see here, JSON 3, Sentinel 6, Saral, ISAT 2 have a quite large spatial distance, track spacing. JSON 3 has 300 kilometers. Even if you have 10 days, but the track is same. So you're not even monitoring most of the water bodies. It won't even intersect. That is why we went ahead with Sentinel 3. Sentinel 6 is also a follow-up of JSON 3. So again, it has same spacing. And Saral Altica is, it is quite complex to process, but we have plans to integrate Saral Altica into mission. So this was one of the limitation that you're still not able to calculate water levels for all water bodies because it does not even intersect the track. The water body is not intersected by track. That is one thing. Other is the footprint. So because it is a radar, it sends a pulse from the satellite, and the pulse is, when it comes down, the footprint of the pulse is quite large. So when you have a large footprint, you are actually calculating from the entire footprint, you are calculating the backscatter. So you might also send signal about the land, about some buildings if there is nearby. So you need to have quite large water body to be able to monitor. And then again, similar to all radar sensors, you have limitations with high winds, rain. If it rains, you cannot measure it, and wave as well. So that is how we do validation. So we calculated water levels, and then we actually took out a time series from the satellite for one of these. This is just for one reservoir, and this is just for one reservoir. On the blue line you see is the actual data from ground sensor, which is monitored by Central Water Commission. It is an Indian government agency which gives you the data of reservoir levels. So you can access this data. So that is the overall thing that we're doing. You can actually access this data via an API, which is actually at API/water quantification and asset ID. More are present in blueskyhq./tutorials. So what do we plan to do next? So far we have only integrated one satellite for water level, which is Sentinel-3 Saral, but we plan to do multiple satellites so that we can cover many water bodies. The challenge there is you have to calibrate. Each satellite comes with its own corrections, and then when you measure the water levels from different satellites, it has a bias. So there is some correction requirement for there as well. So we plan to do that. And ultimately why we wanted to do this is to calculate the volume. we cannot calculate the absolute volume, but we at least know that how much water has changed. There are cases that your water surface decreases. Water surface remains constant, but just the level decreases and vice versa. So you actually, if you want to know if there is water shortage, you have to calculate volume. And that is where we are heading next. So these are the projects which, we are dependent on these. Thankful to all the contributors to these projects. So that's the end. I just want to shout out to my team who is not present here, but Sahil and Ishan were immensely part of this. So thank you so much. I'm ready for questions.